Welcome, everyone. Ever played Tetris or tried to fit all your holiday shopping into one tiny car trunk? If so, you've already grappled with the core concept of today's fascinating topic, bin packing, asterisk. It's a fundamental problem in computer science that deals with how to efficiently pack items of different sizes into a minimum number of containers or bins. We're going to explore the challenges and clever strategies behind this problem, which has incredible real-world applications everywhere, from logistics and manufacturing to data storage and cloud computing. I'm Yaoting Huang, your instructor today from National Chengcheng University, and I'm thrilled to guide you through this intriguing topic. Ready to become a packing pro? Let's dive in. All right, let's polish that transcript for a smoother, more engaging delivery. .. More polished current slide voiceover transcript, asterisk. Now that we've introduced ourselves and the topic of bin packing, let's dive right into what the bin packing problem is. To understand this, let's first look at the asterisk input. The problem starts with "n" items, and each one has a specific size. These sizes, which we'll denote as "A1" through "n" are all greater than 0 and less than or equal to 1. So, "0 less than AI less than equals 1 .. Next, what are we trying to achieve? That's our times time output. Our goal is to find a way to pack all these items into time unit-sized bins. By unit-sized, we mean each bin has a capacity of exactly 1.0. And the crucial part? We want to do this using the time minimum total number of bins possible. To really grasp this, let's visualize it with the diagram you see below. At the top, we have our set of items, shown as blue boxes, with various sizes such as 0.3, 0.2, 0.2, 0.2, 0.2, 0.4, and 0.5. The arrows then illustrate how these items are carefully packed into our bins, which are the green vertical containers located at the bottom. Let's look at the first bin. Here, we've managed to pack items with sizes 0.3, 0.2, 0.2, and another 0.2. Adding those up, the total size is 0.9, which perfectly fits within our bin's unit capacity of 1. Oh, great! Moving to the second bin, you'll see it contains items of size 0.4 and 0.2, giving us a total of 0.6. And finally, the third bin holds just the one item of size 0.5. This visual example clearly shows how items are strategically placed into bins. Remember, our ultimate objective in bin packing is to achieve this kind of arrangement using the absolute fewest possible time bins. Picking up from our last discussion, let's reinforce our understanding of the bin packing problem. Just to quickly reiterate, the problem's input consists of n items, each with a specific size, denoted as _i. As we noted, these item sizes are always greater than 0 and less than or equal to 1. The objective, or the desired output, remains consistent: to find a way to pack all these items into unit-sized bins, meaning each bin has a capacity of exactly 1. And the core goal, of course, is to minimize the total number of bins used. Now let's examine a different scenario, or perhaps a more optimized packing for a similar set of items. Looking at the diagram, we still have 6 items with sizes ranging from 0.2 to 0.5. Our task is still to pack them into unit-sized bins, which have a capacity of 1.0, but here we can see only 2 bins being used. The first bin successfully packs items of size 0.3, 0.2, and 0.5, perfectly filling its capacity to 1.0. And the second bin holds items of size 0.2, 0.2, and 0.4, totaling 0.8. This example truly encapsulates the essence of the bin packing problem. It's all about finding the most efficient way to assign items to bins, ensuring no bin capacity is exceeded, while ultimately minimizing the total number of bins required. It's a fundamental challenge in optimization. Now that we've grasped the fundamentals of the bin packing problem, let's explore its practical applications. On this slide, titled Applications, we'll delve into 2 primary types of problems where this concept is crucial. First, we have scheduling. In scheduling applications, a key characteristic is that the workload for each task is known in advance, allowing for efficient allocation. Second, we have packing scenarios, which are frequently found in logistics and transportation. Here, the idea of bin capacity can be elegantly illustrated with an everyday example: the amount of time that can be stored on an audio CD, typically around 80 minutes. This acts as our bin capacity. To further visualize this packing challenge, let's look at another diagram. Here, we see a set of items represented by blue bars with specific sizes: 0.3, 0.2, 0.2, 0.2, 0.2, 0.4, and 0.5. Our goal, just like before, is to pack these items into bins, depicted as green vertical bars, each having a maximum capacity of 1.0. As you can observe, items 0.3, 0.2, and 0.5 are perfectly packed into the first bin, summing precisely to its 1.0 capacity. In the second bin, items 0.2, 0.2, 0.2, and 0.4 are neatly fit, also totaling 1.0. This clearly demonstrates the inherent challenge of efficiently fitting various sized items into containers with fixed capacities. Building on our understanding of packing problems, this slide introduces a practical solution strategy: the first fit algorithm. Its fundamental rule is quite straightforward. If an item simply doesn't fit into any of the existing bins, the algorithm opens a brand new bin and places that item right into it. Let's illustrate this concept with the accompanying diagram. Here we have a series of items depicted as blue blocks with various sizes such as 0.5, 0.3, 0.4, and more. And as before, each bin has a maximum capacity of 1.0. Following the first fit principle, we begin with the first item, size 0.5. Since there are no existing bins yet, a new bin is immediately opened, and the 0.5 item is placed right inside. Next, the algorithm considers the item of size 0.3. It checks the first available bin, which, in this case, is our newly opened bin currently holding 0.5. Since 0.5 plus 0.3 totals 0.8, and this comfortably fits within the bin's 1.0 capacity, the 0.3 item is placed right into that very same bin. Now let's look at the item of size 0.4. The algorithm, true to its name, time and again times checks the first bin. This bin already contains items totaling 0.8. Adding 0.4 would bring the total to 1.2, clearly exceeding the bin's capacity. Therefore, 0.4 simply does not fit in that first bin. And true to the first fit rule, a new bin is then opened and the 0.4 item is placed there. This precise process continues for all subsequent items. The algorithm always attempts to fit an item into the very first available bin where it can fit, and only creates a new bin if absolutely no existing bin has sufficient space. Building on our introduction to the first fit algorithm from the previous slide, let's now truly visualize its operation. As a quick recap, the fundamental rule of first fit is quite simple. If an item just can't squeeze into any of the bins already open, the algorithm's only option is to create a brand new one just for that item. Now let's see this process unfold using the example provided here. At the top, those blue bars represent our series of items, each with a specific size. And below, our bins, depicted by the green outlines, each have a maximum capacity of 1.0. Watch what happens. First, the item with size 0.5 is placed directly into our initial bin. Then comes the item with size 0.3. Good news! It perfectly fits into that same first bin, bringing its total to 0.8, well within the 1.0 limit. But what happens when the item of size 0.4 arrives? That first bin only has 0.2 capacity left, so adding 0.4 would exceed it. Following that crucial first fit rule, a new second bin is immediately opened, and our 0.4 item finds its home there. Similarly, consider the item with size 0.8. Does it fit in the first bin? No. Does it fit in the second bin, which already holds 0.4? Nope. Since it can't squeeze into either of the existing bins, the algorithm does what it must. A third, brand new bin is created to accommodate this 0.8 item. This visual truly highlights the first fit algorithm strategy. It always attempts to place items into the say the very first available bin it finds, and only resorts to opening a new bin if no existing bin can possibly accommodate the current item. Continuing our look at the first fit algorithm, let's delve deeper into its application with a more comprehensive example. As a quick reminder, its fundamental rule is simple. If an item cannot fit into any of the currently open bins, a new bin is immediately opened to accommodate it. Let's observe this process in action using the visual example provided. At the top, you'll see a series of items, 0.5, 0.3, 0.4, 0.8, and 3 instances of 0.2. Below, we have our bins, each still with a capacity of 1.0, following the first fit principle. First, the item with size 0.5 is placed into the initial bin. Then, 0.3 also fits snugly, so it's added to that same first bin. When the 0.4 item arrives, it no longer fits in the first bin, as only 0.2 capacity remains. According to the rule, a no-knife second bin is opened and the 0.4 item is placed inside. Next, the 0.8 item doesn't fit into either the first or the second bin. This prompts the opening of another KNIME's new bin, a third one, to accommodate it. Finally, the first of the 0.2 items arrives. It perfectly fills the remaining space in the initial bin, completing its capacity. As the diagram now clearly illustrates, we conclude with 3 bins. The first bin is packed with 0.5, 0.3, and 0.2. The second bin holds 0.4, and the third bin contains 0.8. This detailed trace effectively reinforces how the first fit algorithm prioritizes using existing space, only opening a new bin when an item absolutely cannot be accommodated in any previously opened bin. Building on our previous discussion of the first fit algorithm, this slide presents another detailed look at how it works in bin packing. The core rule, as we've established, remains fundamental. If an item doesn't fit into any of the existing bins, a new one is opened and the item is placed right into it. Let's examine the example shown here. We have a series of items with sizes 0.5, 0.3, 0.4, 0.8, and 3 instances of 0.2. Each bin, naturally, has a capacity of 1.0. Now, to fully understand how the algorithm leads to the visual outcome, let's trace the standard first fit process step by step with these items. 1. First, the **0.5 item is placed into bin 1. Bin 1, 0.5. 2. Next, the **0.3 item also fits into bin 1, bringing its total to 0.8. Bin 1, 0.5, 0.3, 3. When the **0.4 item arrives, it does not fit into bin 1. 0.8 plus 0.4 is greater than 1.0. Following the rule, a new bin 2 is opened and 0.4 is placed inside. Bin 1, 0.5, 0.3. Bin 2, 0.4, 4. Then, the **0.8 item comes along. It doesn't fit in bin 1, 0.8 plus 0.8 is too large, nor does it fit in bin 2, 0.4 plus 0.8 is also too large. Therefore, a third new bin 3 is created specifically for it. Bin 1, 0.5, 0.3. Bin 2, 0.4. Bin 3, 0.8, 5. Now we encounter the **0.2 item. It fits perfectly into bin 1. 0.8 plus 0.2 equals 1.0. Bin 1 is now completely filled. Bin 1, 0.5, 0.3, 0.2. Bin 2, 0.4. Bin 3, 0.8, 6. The second 0.2 item comes next. Bin 1 is full, so we check bin 2. It fits. 0.4 plus 0.2 equals 0.6. Bin 1, 0.5, 0.3, 0.2. Bin 2, 0.4, 0.2. Bin 3, 0.8, 7. Finally, the third 0.2 item asterisk arrives. Bin 1 is still full, but bin 2 still has space. 0.6 plus 0.2 equals 0.8. So it's placed there too. Bin 1, 0.5, 0.3, 0.2. Bin 2, 0.4, 0.2, 0.2. Bin 3, 0.8. And there you have it. This precise sequence of steps perfectly matches the visual representation. So, in summary, the first fit algorithm processes items strictly sequentially. For each item, it systematically attempts to place it into the first available bin that can accommodate it. If no existing bin has sufficient space, a new bin is immediately created to hold the item. This example clearly illustrates how items 0.5, 0.3, and one of the 0.2s fill up the first bin. 0.4, and the remaining two 0.2 items then fill the second bin. And finally, the 0.8 item, being too large for any existing partially filled bins at its point of arrival, required its own brand new third bin. Now that we've explored the mechanics of approximate algorithms like first fit, let's broaden our perspective to analyze the performance of bin packing solutions more generally. This slide, titled Analysis, poses two crucial questions. How good is the optimal solution, or OPT, and what is the lower bound of OPT? To set our context, we define A sub I as the size of the ITH item. Below these questions, we find a visual comparison illustrating a bin packing problem, where each bin has a capacity of 1.0. On the left, under APP, representing an approximate solution, we see a set of items with sizes 0.3, 0.2, 0.2, 0.2, 0.2, 0.2, 0.4, and 0.5. This approximate method packs these items into 3 bins. The first bin contains items summing to 0.9. The second bin holds 0.4 and 0.2 for a total of 0.6. And the third bin contains the 0.5 item. Contrast this with the OPT section on the right, which showcases the optimal solution for the exact same DIT set of items. Here, we see a significantly more efficient packing, utilizing only 2 bins. The first bin is perfectly filled with items of size 0.5, 0.2, and 0.3, summing to 1.0. The second bin is also perfectly filled with items of size 0.4, 0.2, 0.2, and 0.2, also summing to 1.0. This visual comparison clearly demonstrates that for these specific items, the optimal solution requires only 2 bins, highlighting its superior efficiency compared to the 3 bins used by the approximate method. Building on our previous comparison, this analysis slide delves deeper into understanding the optimal solution, or OPT, by asking, just how good is it? To set the stage, recall that a sub I represents the size of the ITH item. A crucial insight is this: the optimal solution, OPT, representing the absolute minimum total capacity needed for all items, must always be greater than or equal to the sum of all those individual item sizes. It's a fundamental lower bound. Let's visualize this with another bin packing example. At the top of the diagram, clearly labeled items, you'll see 7 individual items depicted as blue bars. Their sizes are precisely 0.3, 0.2, 0.2, 0.2, 0.2, 0.4, and 0.5. Below them, these items are neatly packed into bins. In this specific scenario, we're using just 2 bins, each designed for a total capacity of 1.0. Notice how the first bin efficiently holds items of sizes 0.5, 0.2, and 0.3, perfectly filling it to 1.0. Similarly, the second bin skillfully accommodates items of sizes 0.4, 0.2, 0.2, and 0.2, also summing up to a perfect 1.0. Ultimately, this illustration powerfully demonstrates 2 things: how the individual item sizes inherently contribute to the overall total capacity needed, and how an optimal solution strives to pack these items with maximum efficiency, always ensuring that the total capacity utilized is at least the sum of asterisk all those item sizes. It truly highlights the fundamental lower bound. Building on our understanding of the optimal solution, this slide shifts our focus to the naive approximate solution, often referred to as APP. The crucial question we're addressing here is, how far off, or how bad, can this approximate solution actually be? To analyze AP, we'll delve into the key properties of a specific algorithm called first fit. A remarkable characteristic of first fit is this. If it utilizes M bins for packing, then a significant majority, specifically at least M1 of those bins, will be more than half full. This logically means that at most one bin can be half full or less. It's a fascinating property, and it begs the question, why? Let's consider the logic behind that. Now, let's illustrate this with an example. Below, you'll see a visual demonstration labeled APP that walks us through the first fit process. We begin with our items, a mix of sizes including 0.5, 0.3, 0.4, 0.8, and 3 separate items of 0.2. Our goal is to pack these into bins, each with a consistent capacity of 1.0. So how does first fit pack them? Let's follow along. The first bin asterisk takes the 0.5, then the 0.3, and cleverly fits in one of the 0.2 items, perfectly filling it to 1.0. Next, the Humsto's second bin asterisk receives the 0.4, followed by the remaining two 0.2 items, bringing its total to 0.8. Since no more items fit into the previous bins, a times new third bin times new the dollars is opened specifically for that larger 0.8 item. In total, we've used 3 bins for this packing. And look, it perfectly aligns with the properties we just discussed. 2 of these bins, the second and third, are indeed more than half full. The first bin, in fact, is completely full. This beautifully demonstrates the principle that at most one bin ends up being half full or less. So how do we prove this interesting property? This slide delves into a proof by contradiction for the first fit bin packing algorithm. Let's begin by supposing the first fit algorithm uses M bins to pack a given set of items. Our core assertion, which we aim to prove, is that if this is true, then at least M1 of those bins must be more than half full. To prove this, we'll use a classic technique, proof by contradiction. Let's assume the exact opposite is true. Suppose there are 2 bins that are less than half full. Look at the left diagram for a moment. Imagine we have one bin with 0.4 capacity filled and another with 0.2 capacity filled. Both are clearly less than half full, since a bin is considered half full at 0.5. Now think about the first fit algorithm. When that 0.2 item was processed, where should it have gone? It should have been placed into the very first near available bin where it fits. Since 0.4 plus 0.2 equals 0.6, which is well within the bin's total capacity of 1.0, the 0.2 item absolutely could have been placed into the bin already containing 0.4. The algorithm would have packed the 0.2 item into that 0.4 bin rather than opening a whole new one. This fundamentally contradicts the core principle of first fit, which always fills the earliest possible bin first. Therefore, our initial assumption that 2 bins are less than half full must be false. This powerfully demonstrates that at most one bin can ever be less than half full, thus fully supporting our assertion that M1 bins must be more than half full. Mystery solved. Now shifting our focus to the diagram on the right, this provides a more general visual example of items being packed into bins using an approximate packing approach, illustrating how various items are allocated to fill bins efficiently. It's another way to visualize these principles in action. Now that we've established a key property of the first fit bin packing algorithm, this slide delves deeper into the analysis of that scenario. Let's first define "A" underscore I as the size of the ith item. Building on our previous discussion, if the first fit algorithm uses "M" bins, a crucial insight is that at least "M1" of these bins must be more than half full. This directly implies that the total size of items within each of these "M1" bins is greater than 1/2. From this critical observation, we can derive a powerful mathematical inequality. The total sum of all item sizes, represented by the sum of (a underscore I) from 1 to (n) must be greater than (m1) divided by 2. This is also equivalent to (app) divided by 2, where (app) represents the total capacity used by the algorithm. This inequality provides a vital lower bound on the total size of items, directly tied to the number of bins utilized. To visualize this concept, let's look at the graphic below. Here, you can see several bins, depicted as vertical green rectangles, with various items packed inside, represented by those blue bars. Notice the dashed orange line. It highlights that a significant portion of these bins, specifically the (m1) bins grouped at the bottom, are indeed filled above the halfway mark, which is clearly indicated by the horizontal black dashed line. The very last bin, the (mth) bin on the far right, is the only one that might be less than half full. Building on our previous observation about the bins, this slide clearly demonstrates why the first fit algorithm earns its classification as a two-approximation algorithm. Let's formalize this. The mathematical derivation hinges on a fundamental principle. The optimal number of bins, denoted as OPT, must accommodate the sum of all item sizes. For the first fit algorithm, if it utilizes APP number of bins, a crucial property, as we just discussed, is that at most, one of these bins can be less than half full. Consequently, the sum of all item sizes is necessarily greater than APP minus 1 divided by 2. Following a series of straightforward inequalities, we can directly see how this implies OPT is greater than APP minus 1 divided by 2. By rearranging this inequality step by step, we ultimately arrive at the powerful conclusion that APP divided by OPT is less than or equal to 2. This final elegant ratio unequivocally confirms first fit status as a two-approximation algorithm. The visual at the bottom once again provides a helpful illustration of this exact concept. Notice the set of bins, specifically the orange dashed box highlighting (m1) bins. The black dashed line within each bin clearly signifies the half capacity mark, powerfully reinforcing the idea that if M bins are used by first fit, then (m1) of them must be filled beyond this halfway point for the algorithm's fundamental properties to hold true. It's a key visual summary of our proof. So, as we've just confirmed, the first fit algorithm is indeed a two-approximation algorithm. This is quite significant. Despite its straightforward, almost naive approach, it strongly suggests that the problem we're tackling can, in fact, be effectively approximated. This naturally leads us to a crucial question. How can we improve upon this? Can we do even better? To see first fit in action, let's turn to the diagram below, labeled APP. Here, each bin has a capacity of 1.0. We observe various items, like 0.3, 0.2, 0.4, and 0.5, being successively placed into the Chavry first bin where they fit. For instance, the first bin ends up with items summing to 0.9, the second bin neatly holds items totaling 0.6, and the third bin contains a single item of 0.5. So in this practical example, we see 3 bins being efficiently used to accommodate all the items, all thanks to this straightforward first fit approach. Building on our previous discussion about the first fit algorithm, let's dive deeper into some key remarks about its behavior, particularly in the context of bin packing. As we've just discussed, the first fit algorithm is indeed a two-approximation algorithm. What does this really mean for us? It tells us that in the absolute worst-case scenario, the number of bins first fit uses will be, at most or never exceed, twice the truly optimal number of bins needed. But why does it perform this way? A crucial factor is that first fit completely ignores the importance or relative size of an item when deciding where to place it. For instance, you'll see in our new visual example how a larger item, say 0.5, might surprisingly end up in a new bin, simply because earlier bins were already filled up with smaller items. Let's take a closer look at simplest diagram to truly grasp this point. Here, we have a specific set of items with sizes 0.3, 0.2, 0.2, 0.2, 0.4, and 0.5. Remember, each bin still has a capacity of 1.0. So, how does First Fit handle these? Let's trace the approach step by step. First, a bin is opened. Items 0.3, 0.2, 0.2, and times another 0.2 are successively placed into this bin. Their combined size? 0.9. Next, the 0.4 item can't squeeze into the tiny 0.1 space left in the first bin. So what happens? A second bin is opened. The 0.4 goes in, and then the subsequent 0.2 item fits right in there too, bringing that bin's total to 0.6. And finally, the 0.5 item, it simply won't fit into either of our partially filled first or second bins. Consequently, a third bin is opened just for that single 0.5 item. This specific example dramatically illustrates how First Fit, despite its straightforwardness, can sometimes lead to a less than optimal packing. That relatively large 0.5 item, instead of being strategically placed, ends up requiring an asterisk entire new bin all to itself. The previous slide showed how the standard First Fit algorithm can sometimes lead to suboptimal packing by not prioritizing larger items. So, how can we improve upon that approach? This slide introduces an important refinement, the First Fit decreasing algorithm. The process is quite intuitive, involving two straightforward yet crucial steps. First, you'll sort all the items by their decreasing size, from largest to smallest. Then, and this is the key difference, you simply run the standard First Fit algorithm using this newly sorted order. Let's illustrate this with an example. Suppose we have a set of items with sizes 0.5, 0.3, 0.4, 0.8, and 3 items of 0.2. Following the first step, we sort them from largest to smallest. This gives us the order 0.8, 0.5, 0.4, 0.3, 0.2, 0.2, and 0.2. Notice how the largest items are now at the beginning. The visual at the bottom clearly demonstrates the very start of this First Fit decreasing process. As you can see, the largest item, 0.8, is immediately placed into the first available bin, which in this case is our initial bin. So we've just seen how the First Fit decreasing algorithm works to find a solution. But how do we truly measure the quality of any given solution, or even understand what the best possible outcome looks like? That's where this slide comes in. We'll be focusing on analyzing the ideal scenario, represented by the optimal solution, which we denote as OPT. Let's start with a foundational concept. We define "A underscore I" as the size of the IDH item. For a bin packing problem, where each bin holds a capacity of 1 unit, a critical lower bound for the optimal number of bins, OPT, is that its numbers must be greater than or equal to the sum of all item sizes. Why is this true? Well, it just makes intuitive sense, doesn't it? The total volume of all items absolutely has to be accommodated. So if each bin holds 1 unit, the number of bins required must be at least that total volume. You can't fit a gallon into a half-gallon bucket, right? Now, let's visualize this with a concrete example. Imagine we have 6 items with sizes 0.3, 0.2, 0.2, 0.2, 0.4, and 0.5. Looking at the diagram, you can see these items beautifully packed into bins, each with a capacity of 1.0. Notice how this specific packing solution uses only 2 dial bins. The first bin perfectly holds items with sizes 0.5, 0.2, and 0.3, summing perfectly to 1.0. And the second bin neatly contains items of sizes 0.4, 0.2, 0.2, and 0.2, also summing to 1.0. This is an incredibly efficient packing. All items are perfectly accommodated within these 2 full bins, providing a clear illustration of what a potential optimal solution could look like for this set of items. Building on our analysis of optimal solutions, this slide delves into an asterisk approximation solution. Specifically, we'll examine the behavior of a particular bin, the time b-die-th bin, within the context of the APP algorithm. When analyzing this time b-th bin, we actually encounter two primary distinct cases we need to distinguish. First, case 1. This occurs when bin tours holds at least one item whose size is greater than 1/2. Take a look at the image on the left. It vividly illustrates this scenario. Here, the bin contains an item of size 0.8, which clearly satisfies this condition. Then we have case 2. This is when bin tie b does not ties contain any item larger than 1/2. You can observe an example of this scenario on the right, where the bin holds an item of size 0.4. Okay, let's polish this up for a smooth conversational flow. -- ... Polished current slide, voiceover transcript, ****. Now let's dive deeper into case 1, which is when bin time contains an item whose size is greater than 1/2. What does this condition imply? Crucially, it dictates that every time bin prior to bin must also contain an item with a size greater than 1/2. Because of this, each of these larger than half items must be placed into its own separate individual bin. This leads us to infer that the optimal number of bins, or OPT, must be at least dompt b dompt nop I. Let's look at the visual representation now. Here, we're seeing a total of 5 bins. Notice how the first 3 bins each hold an item of size 0.8. The third bin, highlighted in orange, is our specific bin times b u doms. And you'll see the 2 bins directly before it also contain items of size 0.8. All 3 of these items, the one in bin, point, and the 2 before it, clearly satisfy the condition of being greater than 1/2. Following these, we have 2 additional bins, each containing an item of size 0.4, which, as you can observe, are not greater than 1/2. Now let's shift our focus to case 2. Here, bin times beach2 presents a different scenario. It does not contain any single item with a size greater than 1/2. This condition leads to a crucial observation. Each of the bins times bin times bin times b note will contain at least 2 items. This holds true with the possible exception of the very last bin in the sequence. Furthermore, when we consider the bins handled by our approximate bin packing algorithm, or APP-B, these bins collectively contain a total of at least 2 times APP-B items. To illustrate this, let's look at the example bins shown below. You'll see several bins, each with a total capacity of 1. In this particular setup, the first 2 bins happen to contain a single item of size 0.8 each. Now let's focus specifically on bin times b times, which is outlined in red, and the bins that follow it. Bin times b times itself is packed with 3 smaller items, 0.2, 0.2, and 0.4. Notice how none of these individual items are larger than 0.5, perfectly aligning with our case 2 definition. The subsequent bins also clearly demonstrate this principle, being filled with multiple items. For instance, the very next bin also contains items of 0.2, 0.2, and 0.4, summing up to 0.8. Continuing our exploration of Case 2, let's now dive deeper into a specific scenario, Case 2a, which focuses on instances where the value of "" is considered small. The central point here is that a particular set of bins, referred to as the APP-B bins, collectively contain at least 2 times APP-B items. So what defines B as small in Case 2a? It's when B is less than 2 times APP-B. This condition has a significant implication. Imagine if we were to hypothetically add, 2 times APP-B items to every bin prior to bin B. This action would result in B-1 foot overfilled bins. Consequently, the sum of all item sizes, denoted as A sub I, would be greater than B-1 foot. To visualize this, observe the bar charts at the bottom of your screen. These represent individual bins. you'll notice many bins display a total fill level of 0.8. The bins specifically associated with Grade A are highlighted. Inside one of these highlighted bins, you can clearly see individual items with sizes 0.2, 0.2, and 0.4. Together, these perfectly sum up to 0.8, illustrating exactly how items are packed within these bins under Case 2A. Building on our discussion of Case 2A, this slide introduces Knives Case 2B, Knives Tamply, where the variable B is now considered knives large, knives, knives. Similar to our previous case, the bins associated with our approximation -B, or APPB bins, still contain at least 2 times APPB items. However, the crucial distinction for Case 2B is that B is defined as large when its value is under greater than or equal to 2 times APP***. A significant consequence of this larger B is that these 2 times APPB items can actually be assigned to a different das bin, which we'll refer to as AP prime, a bin that is inherently smaller than B. This strategic assignment then leads to the creation of 2 times APPD overfilled to D. Mathematically, this means the sum of item sizes, denoted as a sub I, is greater than or equal to 2 times APPB. Now let's turn our attention to the visual illustration at the bottom. Notice the series of bins presented here. On the left, indicated by the ellipsis, are multiple bins, each consistently filled to 0.8 capacity. To the right, prominently outlined in red, are 2 specific bins labeled Within each of these B bins, you can clearly see 3 individual items, 0.2, 0.2, and 0.4, showcasing how they are packed. Having analyzed the specifics of cases like 2B and the characteristics of bins like B, this slide now brings together a comprehensive summary of our key findings. We begin with a fundamental observation. The optimal solution, or OPT, is always greater than or equal to the total sum of all item sizes, which we denote as a sub I. Now let's delve deeper into the conditions we've uncovered. We've observed that either OPT is greater than or equal to B, OR. The sum of all item sizes, A sub I, is greater than or equal to 2 times APPB. This leads us to a crucial refinement, highlighted in red on the slide. Specifically, either OPT is greater than or equal to B, OR, OPT is greater than or equal to 2 times APPB. This particular relationship, as we've seen, hinges on whether a specific bin, labeled A, contains an item larger than 1/2. Our overarching goal, however, is to arrive at a general conclusion that holds true universally, irrespective of the specific characteristics of bin B itself. Now let's shift our focus to the visual illustration at the bottom. This diagram vividly demonstrates an optimal packing scenario, clearly labeled OPT. Here we see a collection of items represented as distinct blue blocks, with individual sizes listed as 0.3, 0.2, 0.2, 0.2, 0.2, 0.4, and 0.5. Notice how these items are then optimally distributed and packed into just 2 bins. The first bin efficiently aggregates items of sizes 0.5, 0.2, and 0.3, perfectly filling its capacity to 1.0. Similarly, the second bin neatly contains items of sizes 0.4, 0.2, 0.2, and 0.2, also perfectly summing to 1.0. This concise visual example beautifully showcases the power of efficient allocation when placing items into fixed capacity bins. Building upon our understanding of optimal solutions and the conditions we just discussed, this slide delves deeper into the crucial concept of asterisk lower bounds for OPT, which, as we know, refers to the optimal solution itself. First, For any B which represents a number of bins or a similar parameter, the lower bound of OPT is often considered the worse or lower one. This is primarily due to the nature of worst-case analysis, where we prepare for the least favorable outcomes. This type of analysis is absolutely necessary because we often cannot be certain if a particular BTH bin will contain a large or a small item, which significantly impacts the packing. As an illustration, the slide mentions Y2 being picked over Y1 foot, indicating a strategic choice based on specific item properties or perhaps their size ratios. Second, for any given input, the lower bounds of OPT are comprised of several important conditions. Among these, a particularly significant one is the condition that OPT is greater than 2/3 of APP, where APP, in this context, likely denotes an approximate solution. This specific inequality is truly a key takeaway. Now let's turn our attention to the graph at the bottom, which visually explains these crucial relationships. The x-axis represents B, our number of bins or parameter, and the y-axis clearly shows the lower bound of OPT. The red line, vividly displayed, illustrates the condition that OPT is greater than 2 times the quantity APP minus B. Notice how, as quote increases, this particular lower bound conveniently decreases. Conversely, the blue line represents a simpler yet equally important condition, that OPT is simply greater than B. As you can see, this lower bound increases linearly with B. These two lines intersect at a truly crucial point on the x-axis, which, interestingly, is precisely 2/3 of APP. This intersection signifies exactly where the constraining lower bound shifts from one expression to another, defining a critical threshold. Finally, the shaded area, extending from B equals 0 all the way up to APP, represents the region constrained by these combined lower bounds. It beautifully helps us visualize the feasible range for B, and precisely how these inequalities collectively define the space for the optimal solution's lower bound. What a clear illustration! Polished current slide voiceover transcript. All right, building on our previous discussion, this slide consolidates the key findings from our analysis. Let's revisit the 2 essential conditions we established for the optimal solution, OP-PT. Either OPT must be greater than B, or OPT must be greater than 2 times the approximate solution minus B. By setting these 2 conditions equal, specifically solving the equation where B equals 2 times APP minus B, which, as we saw on the previous slide, represents their intersection point, we arrive at a crucial derivation. B is equal to 2/3 of the approximate solution, APP. This leads us directly to the fundamental conclusion that OPT is greater than 2/3 of APP, a relationship that holds true universally, regardless of the specific item distribution or the BTH bin's contents. As a powerful and direct result of this, the ratio of the approximate solution to the optimal solution, APP over OPT, is guaranteed to be less than 3/2. This wonderfully demonstrates that we have successfully achieved a 1.5 approximation algorithm. Now let's turn our attention to the diagram at the bottom, which illustrates a practical example of bin packing in action. Here, we observe 6 items with various sizes, 0.3, 0.2, 0.2, another 0.2, 0.4, and 0.5. Notice how these items are efficiently distributed into 2 bins, each with a total capacity of 1.0. For instance, the first bin perfectly accommodates items sized 0.5, 0.2, and 0.3, completely filling its capacity. Similarly, the second bin neatly holds items sized 0.4, 0.2, 0.2, and 0.2, also completely filling its capacity.